Example 3.3. Label the angles θ1, θ2 in the diagrams to indicate how we would apply Snell's law to them. We also indicate whether n1 or n2 has a larger value. Notice these two diagrams are identical except for the direction of the light rays from n1 to n2. This is from n2 to n1. Otherwise, the angles are the same. Okay, so when I label the angles, θ1 the same, and these are angles measured from the normal, and θ2 are the same. Okay, just now we have to decide which refractive index, n1 or n2, has the larger value. So as we analyze the first diagram, right? Okay. First diagram is from lower refractive index, n1, to a higher refractive index, n2. That's why it bends towards the normal instead of going straight. Okay. What if the light ray is going in opposite direction? This way, and this way, bending away from the normal. This will mean that the first medium must have a higher refractive index, and the second medium must be a lower refractive index. That's why it bends away from the normal. So n1 must be larger, n2 must be larger than n1. And in the end, our conclusion in both cases are the same, regardless of whether the light ray goes from first medium n1 to n2 or in the reverse direction from n2 to n1. So in this, when we apply Snell's law, n1 equal to sine θ1, n2 sine θ2, this does not require us to know whether from which medium is the incident ray or happening, right? So is it in the incident ray in the first medium, or the incident ray is in the second medium? You still can apply Snell's law correctly. This is because the light ray can travel along the same path regardless of which direction it started from, and we call this the principle of reversibility.